Hello everyone and welcome to this presentation about the following subject, how to translate C program to PlusCal for model checking of safety properties on source code. So my name is Guillaume FATTA and this presentation was made in collaboration with Amira Metni and Emmanuel Oraillon for the Asterios Technologies company. So to place a bit of context, I'm a student currently in final year of Master of Science at Centrale Supélec Paris-Saclay University in France, and I'm currently in a gap year in which I have to do two internships of 5 months, and one of those internships took place from October 2024 to March 2025 about the following subject: the modelization and formal verification with TLA plus and TLC of real-time synchronous algorithms of Asterios Technologies microkernel, and it was supervised by Emmanuel Oraillon and Amira Metni. So in this presentation, we'll present the tool that we made, the different details of implementation, and how we manage memory in this tool. Then we will see the results that we had and the limitation and perspectives. And finally, we will conclude about our work. So a bit of introduction and context to begin. Asterios Technologies is a company that is a subsidiary of Safran Electronics and Defense, and it provides software solutions to orchestrate, integrate, and certify critical real-time applications. So these solutions are meant to run on embedded system with a microkernel that is developed directly by the company. And the idea of the internship was to use TLA plus to verify multi-core algorithms, which are real-time and critical. So with this internship, we use TLA plus for multiple purposes and experimentation. We made some classical formal specification, but we also tried to write specification directly from the source code. So one of the source code that we tried to verify was the implementation of the scheduler of the kernel. So uh, making this verification directly from the source code allows us to verify simultaneously various configurations at once with TLC, and it avoid to do manual tests, which could not be exhaustive and long to write manually. So the idea is really to see what can be achieved and to experiment. It will not be used directly in the company verification process. And so we had with this scheduler example the idea to make some automated translation directly from the code. So this approach is possible because the C code that is written is simple and embedded on a microkernel, so we don't have libc or dynamic memory, something like that. So it is really a simple C code that we can imagine to translate directly into TLA+. So the main motivations of our work was a previous work made by one of my supervisor, that is Amira Metni. So during her PhD thesis, our subject was C to TLA+, an automated translation from C code to TLA+. Also, the scheduler that we try to translate is a relatively concise code with a simple and clear structure, so it is convenient for us to translate it. And we had some first successful small translations by hand that gave us hope to make this work. So we really wanted to revive and rehabilitate this old project, with the main difference to translate the C code to a PlusCal target instead of TLA+. So why we chose to translate to PlusCal, it is because we can use the language paradigms that are closer to C than TLA+. And the transpilation of the word scheduler source code is one of our objectives in this work. To see if the verification of the scheduler could be interesting for the company, we tried to find a non-bug in an old version of the scheduler source code with TLC model checking. And we also want, with this translation, to describe invariants on the implementation to verify code properties that we want the scheduler to verify. So the main idea of all this is to automatize the translation of C programs in PlusCal to facilitate their verification. So now I will present a bit the tool to use. So that the tool is called C2 PlusCal. So to write it, we used Pharmacy. Pharmacy is a set of interoperable programs to analyze C programs. It is used to preprocessed C program to seal representation and retrieve the AST. So I will present later what is the seal representation and how it can help us to achieve what we want. So Pharmacy is written in OCaml. That is a functional language used to make the plugin that we want. And we designed a new personalized intermediate representation for the program to translate it to PlusCal. So the workflow is this one. We take the C code that we preprocessed with Pharmacy to have a seal representation. Then we use our plugin to translate the seal representation to a PlusCal intermediate representation. And then this PlusCal intermediate representation is used to generate a .tlf files, that is the PlusCal specification, and a .cfg file, that is the TLC configuration. And then we can use the TLC model checker on the specification that is generated. So how do we represent a C program in our translation? So a C program is for us a collection of global functions and variables. And we will use sequences to represent memory. So, for example, functions will be translated into PlusCal procedures. That is convenient for us because the arguments are passed directly, and we have an automatic return flow of the program, but it does not support return values as real C functions. We will have in our PlusCal translated verifications different memory locations. So a memory that will be shared between all the procedures and processes, that is called mem. A memory that will be used for local variables, that is called mystack. And a memory that is used for return values, that is called wet. So the idea is kinda to write a naive C interpreter with a stack in PlusCal, so that will run the C program as we want it to run in a PlusCal verification. So I will take a little example to be more clear. So if we take here the C code that is on the left of the screen, so we see that at the beginning of the program, we define two global variables that are x defined to 0 and y that is not defined at the beginning. So here we will have the mem section of the memory. So that is the section that is used to share variables between procedure and processes. So we will store the global variables in it. So at the beginning, we will store the value of x, that is 0, and the value of y, that is a non-def value. Then if we go into the main function, we see that the value of y is changed to 2. So we will change it in the mem section, and then we define a name variable that is local to the main function, and that will have the value returned by the main function. So at the beginning, we will define the m here, the m variable for the main function as undefined, and then we will call the main function to compute its value. So if we enter into the main function, we see that we will have two new local variables that are a and b. So a and b will also be stored in the mystack section here, and they are defined as the arguments that we passed to the main function. So here x, that is 0 for a, and y, that is 2 for b. So they will be added like that in mystack. And then in the main function, we will return the value a plus b divided by 2. So we will add this value into the wet stack here. So the value is 1. And this stack here will be used to change the value of the m variable in the main function. So it will be used like to simulate the return values of C functions. So when we finish PlusCal procedure, we will push the return result into the wet stack, and then we will pop it if we have to use the value that we want. The value that is returned, we will pop it directly from the wet stack that is convenient. So for example, here we push 1 on the return stack, and then when we return in the main function, we will pop the 1 value and update the m value in the main function. So that is a little example of a C program, like how we will interpret a C program into our PlusCal representation. So we saw that we use some different memory location. So to represent C variables, we will use pointers. So variables will be represented as pointers to their values in the memories. And PlusCal macros will be defined to load and store directly from the memory. So when I say that variables will be represented as pointer, I mean that a variable, like a C variable, will be represented in the PlusCal verification as a record with 3 fields. So a field that is called loc, that is the memory region where the variable will be stored. A field that will be the frame pointer in this region. For example, in my stack, we will have a frame pointer for each function call that we have, and then an offset from this frame pointer to point directly to the values that that represent the variable that we want. So if I take back the example that I showed you, here, for example, we would represent the y value as this, so the y global pointer, so global because it is a global variable. Its location here is mem because it is stored in the mem stack. Its frame pointer is 0 because in the mem stack we don't have any function, so we don't use the frame pointer value. And its offset is 1 because it is placed at 1 of offset into the memory section. And for example, the m variable of the main function, its location will be my stack because it is located in the my stack section. Its frame pointer is 0 because the main function it is as a 0 frame pointer, and its offset is also 0. So with this representation, we see that we can define some pointers directly into the different memory sections of our program. So we will, as I said, we will define several PlusCal macros. For example, a load macro that will be used to retrieve a value from the stack. So this macro will be defined as a TLA plus operator because it needs to represent a value. For example, if I write load x pointer, it needs to represent directly the value that is pointed by x pointer. So to do this, we need to use a TLA plus operator to define this macro. We also have a store macro to put a value in a stack at a pointed place. We also have a wait at value macro that is used to retrieve the last return value on the wait stack. So that is used, for example, for the a equal f of x expression. And we have a decl macro, so to initialize the pointer at the right value and add it on the stack on the beginning of the procedure, for example. So if I take a whole example of a little C function translated to PlusCal by our tool, it is how it presents. So we have here a little C function that add 2 to an integer x that is passed by argument. So here we will translate this function with a procedure, as I said before, that also have the x argument. So the variables of this procedure are the 2 variables that are used in the C function, so x, and here we define a y variable. So x pointer and y pointer. So those 2 will be located on the stack. We define their frame pointer and their offset as the length of the stack and 0 because they will be redefined here with the decl macro. So for example, here we put dec x82 x pointer 82. It is used to store the value here that is passed as argument to the procedure into the x pointer variable. And it also will define the frame pointer and the offset as the correct as with their correct values to have the pointer that point directly to the good place into the stacks. We do the same with y with an indef value at the beginning, and just after we will store 2 here into the y pointer, just so to have here integer y equal to. And then we translate directly the function as it is written. So for example, x plus equal y. So we store into the x pointer the value load of x pointer plus load of y pointer. And then to return x, we push the value of the x pointer on the wet stack. And at the end, before returning the procedure, we just pop the two variables that we defined from the stack. So that is how we translate a simple C function directly into PlusCal, and we see how the program flow will work. But at the beginning of the PlusCal verification, so how do we manage global variables? They will be initialized in a separated process. So we will have a PlusCal global flag to prevent the beginning of other processes before the end of initialization. So that is implemented because at the beginning we wanted to automate the translation of different threads in C programs, but we didn't have the time to do it. So for the moment, we only have one other process into the program that will call the entry function of the C original program. But at the end, if we want to translate different C threads into different PlusCal processes, we will need another process that will initialize the global variables that will be shared between the different processes. So that is the meaning of this initialization process and this PlusCal global flag that will prevent the beginning of other processes before its end. So it is how it looks like into the PlusCal translated verification. So here we have a fair process global init that will do the initialization of global variables and then put the init done variable as true. And then we will have other processes that will await for init down to be true, and if it is the case, they will do their job. So, for example, here to call the main function. So this was a bit of presentation of our tool. Now I will explain the different implementation details. Also, how do we implement some C parallels. So, as I said before, we use pharmacy that is used to preprocess the C program into a CIL representation. So, what is the CIL representation? It is a preprocessing of the C program, as I said. And, for example, it will transform any loop into a while one with break labels and go to simulate the job of the tool of the loop. So why is it convenient for us? Because in PlusCal we only have while loops. So for example, here with pharmacy, the four loops will directly be translated into while one loops, and we then can use a direct translation from this while one loop into PlusCal while loops, because in PlusCal we also have goto statements. So we can also translate directly the goto statement and the break labels that will be used, that will be generated by pharmacy. Also, the C representation is used to change the expression that contain side effects and to separate them into different statements. So that also will be convenient for us. So, for example, how do we translate a for loop in a C code into a PlusCal verification? So, for example, we have here a little C loop that increment J variable. So it will be preprocessed by pharmacy into a while true loop. that we will translate directly in PlusCal. And then here we'll have an if-else statement to simulate here the loop condition. So if the j variable is lesser than 10, we will skip, so we will continue the core of the loop. And if it is not the case here, we will go to the while one break label that is after the while loop. So that will simulate the loop condition and how do we go outside of the loop. And then here it is just the core of the loop that it's directly translated into PlusCal. Also, how do we translate complex data structures such as arrays or structures? So arrays are represented as sequences into PlusCal, and structures are represented as records. So for example, if I take a little struct here and say that is an error with a field name and a field ID. So I can define here and see a variable global error that has a name test global error and an ID of 1. It will be translated directly in PlusCal by this variable global error is equal to field name test global error and ID field to 1. So as for the loops, it is very convenient because we directly can translate so arrays and structure into PlusCal without doing some weird things. So we can do the translation directly. Also, it is feasible because, as I said, we are into our context in a static context, so the arrays are already allocated with a fixed size, and the initialized arrays are filled with undef values. So here we have a procedure in PlusCal that is used to initialize the arrays. So we pass to it the size of the array and the pointer that should represent the array into the program. And it will use a while loop with a global variable here to fill the array with the correct number of undef values. And then we can, this is the way that we simulate the pre-allocation of arrays in our memories. Also, our pointer representation of variables allows us to do some pointer arithmetic. It is also convenient because, as I said, we represent arrays with sequences and structure with records. So all the data types in the stacks will have a size of 1. So it is convenient for us for the pointer arithmetic because we don't have to bother about the size of the data. So what we can do is that we can add some integers to pointers, or we can add or subtract two pointers with each other. For example, here I have a little C code that take an X pointer and add 1 to it. So how do we do this in PlusCal? So we store the value of X into the X pointer, and then we change the X pointer by doing this operation. So we take the X pointer, except that this offset will be changed by its offset incremented by 1. So this is how we manage a simple pointer arithmetic into our PlusCal translation. So those were some details of implementation. So we saw how we manage some CPAR readings as complex data structures, loops, or pointer arithmetics, but I need also to explain to you how we manage memory at the end in our tool. So as I said, we use some pointers, like we represent C variables as pointers, and we represent the complex types as sequences or records. So this will simplify for us translation, and it allows us to all data types to have size of 1. But the current pointer representation that I presented to you has several limitations. So it prevents us from taking the address of struct fields or array elements, and it does not always correctly handle expression like star star of X. So what do I mean by this? For example, Here, if I represent an array in my PlusCal representation with a sequence, I will store directly a sequence into one of my stack into the PlusCal verification. And then if I want to define in a pointer to an element of this array, I cannot do it because my pointer will only have informations about objects that are stored in the stack. So what I can do is that I can define a pointer that point to the sequence representing the array in the stack, but I cannot say that I want to take in this sequence for example, the first element of or the second element. So I cannot have pointers directly to indexed element, and that is the same problem for fields into structures. So these issues become particularly problematic when dealing with nested structures or arrays that involve pointers. So we needed another representation for pointer to solve this issue. So we define another representation for pointers, but it will not replace the previous representation that I presented. It will be added to it. So we will have pointers that use the first representation with the location, the frame pointer, and the offset. And we will have other pointers that will use this new approach that I will present. So this new representation use new fields. So for example, a field PTR that represents a pointer that points where the element that we want to retrieve from is stored, and a ref field that is a referent to the target element that we want at the end, such as the field name or the index into the array that we want to have. So for example, if I here take a pointer to a field into a structure here, um, what I can do is that I can translate it in PlusCal like this. So I will have here a pointer with the new representation. So its PTR section will be initialized with the base pointer of the expression here, so error pointer. And the reference, so the ref field, will be stored as ID. So this is because we want to retrieve here the ID field of the structures. So with this representation, we can now take addresses from new elements that we cannot before with only the previous one representation of pointers. And it will help us to simplify and homogenize access to arrays elements. So for example, here, if I want to do this in C, so array of x is equal to 3, what we did before is that we loaded the array pointer, and then we took the x index of it, and we stored 3 into it. But now with our new representation, we can write directly this. So we can define a new pointer that take as base pointer the pointer to the array that we want. And then the reference is only the index of the element that we want to change. So here the index is x. And we can directly store 3 into it, so that homogenized the way that we store elements into the stack. So by using only store macros in PlusCal. So to support both pointer representation, we need to modify the macros that we defined earlier. So here is the way that we defined the load macro to support both pointer representation. So we use a recursive here definition to trace back to the base pointer of an expression. So it is used to trace back all the PTR field of the pointers that can be nested. And then when we come back to the base pointer, we use the previous load definition. So by taking here into the right memory section the good emplacement by basing on the offset frame pointer and length of the current stack. And then when we have retrieved this base pointer, we just take here into TLA plus the reference to the element that we want. We also can redefine the store macro So here is the complete definition. So if I analyze it a bit, the store macro will use two TLA plus operator. So the first one is index sequence. So it will be used to retrieve the sequence of indexes to access the element. So for example, if I have a pointer to a field into structures as in the previous example in C, here, the index sequence of this pointer will be the pointer to the structure that we want, and then the name of the field that we want to retrieve. And then we use an update stack operator to update the corresponding stack based on the sequence of indexes to access the element that we want to retrieve. So these two operators are recursive and are used as for the load operator to trace back to the base pointer of the expression, and then the update stack to do the reverse way and to update the stack from this base pointer to the indexed element that we want to change. So now that I present how the tool works, I will show you what our results were, the limitation that we found, and the different perspectives for the project. So here are the experimental results on the scheduler source code. So the bug that we searched at the beginning, that was a non-bug in an older version of the scheduler source code, was found with an handwritten translation. So as I said, the tool that we developed was part of a 5-month internship, and it was not the main subject of it. So we didn't have a lot of time to develop it. So the tool is at this time very incomplete. So it cannot be used on the whole scheduler source code to generate a working PlusCal verification. So what we had to do is that we can use the tool to translate some functions of the scheduler source code, and we need to translate some other parts by hand because they are not handled by our tool. But by doing this, we managed to find the bug that we searched. It took approximately 45 minutes of verification with TLC on 10 cores of an Intel Core Ultra 9 processor. So it is quite fast when we compare it to the time that the manual test would have took to write and to run. And the proposed invariant that we use to find the bug is quite intuitive and could have been written without prior knowledge of the non-bug. So we could imagine a scenario where this PlusCal translated verification could be used directly to write some intuitive invariant on the code and find some bugs that we didn't find by hand before. But there are still several limitations to this experiment. So, for example, the generated PlusCal verification is quite long and verbose, so it is difficult to read it and to write property on it. And we also had to write some arbitrary abstractions, for example, for the hardware specificities. And those abstractions lack proximity to the original source code, because I remind that the main objective of this tool was to be as close as possible to the source code to make some verification on it. Also, the tool has several limitations by itself. So, for example, I didn't mention it, but at each PlusCal line that we write, we add a PlusCal label. So we have an explosion of the state space because we have a lot of transitions between states of the program. Also, the labels that are generated by pharmacy, for example, for the while loops or the nested if-else statement, may have duplicated names, and we didn't have the time to handle this issue. Also, we have an incomplete management of certain pointer operations and arithmetics and pointers, and some syntactical construction of the C language are not handled, such as the type of, size of, switch, and so on. But we have different possible evolutions for the project. For example, as I said, we want it to handle different threads in different PlusCal processes, and the project is open source, so we can imagine to have a future for this project with contribution. So to conclude, as I said, the initial goal was to play with PlusCal and TLA Plus in the internship and see what can be done. The idea was really to experiment and not to have some tools that will be directly used in the industry. And we managed to have an automated translation as an experimental approach, but it shows promising results. And it shows promising results. And for the perspectives of the project, we didn't at the moment explore the use of TLIPS on the translated specifications to make some real proof on the source code. Also, we only used TLC as the model checker, and we didn't try to use Appalach. So to compare, for example, the performance with TLC, maybe it could be better for us. And finally, one of the ideas that we had, that we didn't have the time to try, is to show that the translated specification refines an abstract specification. So, for example, to show that the source code respects an abstract specification of the model that we want. So, as a final conclusion, I want to say a big thank you to the Asteos Technologies team for their warm welcome during my internship and their support throughout it. And a special thanks to Emmanuel Ohayon and Amir with me, so my supervisors, for their guidance and advices, and for their help to do this presentation and the C2 PlusCal tool. And as a final word, if you would like to stay in touch with the project or check out some of my other projects, my LinkedIn is available. So my name is Guillaume FATTA, and I also have a GitHub account with the username Atafi. So big thank you to you for your attention, and if you have any question, feel free to ask them.